John, we know where next week? For your presentation?
It's a week from.
Yeah, so where?
There is a room, I forget what number it is, but I'll let you know.
It's still time.
Yeah. It is set though.
Okay.
This is the basic time of the year.
Yeah. Everybody is speaking.
That's right.
You have also students.
I have, let's see, it's still to present. I have
Wow.
one fact. Just that outline the foundational functions.
Still waiting for Professor Escobar to join. We'll be in room 115 in the math department.
Oh.
Yeah. Yeah, it's quite good. It's been my Bible for a while. It's been there's the Donaldson and Convent have that format. Let's put it to a side. Just have those two that I go back and forth. Okay. Professor Escobar is in Zoom now. And so my thesis topic.
Wait, I need to introduce you. Okay, so welcome everyone to our talk, our presentation today. So Anthony Hong is our speaker. So he's reporting his undergraduate research in the last almost 1 year, starting from last spring this time. So he will report about symplectic geometry, reduction, convexity, and unimodularity. So please.
So I will talk about cover the basics about the symplectic geometry and talk about the three classical theorems. Marsden-Weinstein-Meyer Theorem, Atiyah-Guillemin-Sternberg Theorem, and Delzant's classification theorem, and then do some applications for that. So suppose we have a smooth manifold angle. And we have a vector model over that. So when we say geometric structure, we are often saying that a smooth section have a tensor bundle. Well, it can be written as this in a fancy form. And a usual example, the familiar one, is the Riemannian manifold. Where for each of the points you assign an inner product and do this smoothly. And the topic for this presentation is about the symplectic geometry. Symplectic manifold. Where instead you still assign forms for each of the points, for each of the tangent spaces Tm. But now this omega p, it is still bilinear, of course. But now it is not symmetric. It is instead skew symmetric. What this means is that if you swap the two entries, it will give a negative sign. And this implies that if you put the two entries to be the same, it will be 0. So there is a bundle of vectors making that 0. And to remedy this, well, because for inner product you have definiteness, which means this is 0 if and only if and only if this is 0. To remedy this, we instead ask for non-degeneracy. This means this map done by this is inject. That is its kernel is 0. And to add some global robustness for this structure, we also require this form to be closed. So the exterior differentiation of that is 0. There are also almost complex structures and Kähler structures. And for Kähler structure, where all of these structures come together compactly. And there are some simple examples of symplectic manifolds. The fundamental one is the complex space, which is just 2n-dimensional Euclidean space, where the standard symplectic form is given by this. It can be identified as this using for the complex coordinates. And cotangent bundles, well, this is a typo here. It is not torus. The cotangent bundles are also symplectic manifolds. And there are also some algebraic objects like flags. They can be attached with symplectic structures. This pictures shows how symplectic geometry is positioned among other geometries. So we can see that symplectic manifold is smooth, of course. It has even dimension. That's due to the non-degeneracy. And it is orientable. That's because if you take the nth exterior power of omega n, this is a top degree form, and it determines an orientation before n is orientable. Now, the second fundamental definition for this presentation is the Hamiltonian G-space. So just as any mathematical areas, we are concerned with the classification of the objects we just defined. So what's the classification for the symplectic manifolds? We need to have a notion for that. So given two symplectic manifolds, to say they are the same, we need a diffeomorphism to preserve the smooth structure. And it also needs to preserve the symplectic structure, which means the pullback of the second form is the first form. That's a symplectic topomorphism. And suppose we have a Lie group G acts on this symplectic manifold by the symplectomorphisms, where this symbol refers to the group of all of the symplectomorphisms. And Then this space is called Hamiltonian G space if we have a moment map. Mu, encoding all of these Hamiltonian actions via the Lie algebra. The moment map is defined by using these two conditions. The first one is the Hamiltonian condition, where for any element of the Lie algebra, we can consider this smooth map called the moment map along X. It is defined by this for each of the points, where this bracket is called the natural period. And so this Hamiltonian conditions requires that differentiation of this is equal to this. This form is defined by this. And this is a vector field. It is the vector field generated by the one parameter subgroup by X. Explicitly, this means and the second requirement is called the equivariance condition, where you have this condition for each of the elements of G. So this symbol means the co-adjoint representation. So the co-adjoint representation is defined as the adjoint of the conjugation representation. And the conjugate representation means the differential of the conjugation by element G. The differential of this. So a whole bunch of definitions seems to be a bit esoteric. We will see some of the examples first to familiar with this concept. The first one is the sphere. So consider a two-dimensional sphere, and we have the spherical coordinates. This gives the charts, and this is x-axis, y-axis, and z-axis. Take out the z-axis to call that height. You find that it's the height function for each of the points. And the standard symplectic form on this is then simply defined like this. We recall for Rn, R2n, the symplectic form is defined like this if n is 1. Now, so we want to give a Hamiltonian G space structure for that. So consider the circle action. The circle acts on the sphere by rotation, by the horizontal rotation. So for each of the points I theta, you rotate by theta on the sphere for each of the points. So if this is a point on the sphere, after the action is positioned as here. So we can observe that the height of the original point and the new point are the same. So the height is preserved. And this hints us to say that moment map mu for this action is just the height function. That's because for abelian group, abelian Lie group, the equivariance condition for abelian Lie group, the coadjoint representation is the identity. Therefore, the original equivariance G condition becomes the invariance condition. And we have seen that the height of the new point is equal to height of the original point. So the second condition is verified, and we want to say the first condition is also true. That's by standard computations. The first one is the Hamiltonian condition. So from this figure, we see that the flow lines of the actions are the latitudes. And these float lines naturally, if you want to take the tangent vectors of them, you get the differential by theta, differentiation by theta. That's because only theta is changing for each of these latitudes. So then we compute this. By definition, this, and by definition, it's just 1, this is equals to 0, therefore, this is the h, which is the differential of the height function. Therefore, the Hamiltonian condition is also verified. Therefore, the height function is a moment map, and the circle action is gives sphere a Hamiltonian G-space structure. So I will talk about the sketch of the groups of the three theorems in this presentation. The reduction theorem, convexity theorem, and unimodularity theorem. And I would like to say something about the motivation behind this thesis. So I first learned this formula, Polyakov-Khovansky formula, in Professor Escobar's course, topics in polytopes. And this is very interesting for me. And so they consider this perturbated polytope and apply Todd operator to that to compute the number of integer points in a polytope. This is their formula. The number of integer points in this polytope, this is the number of them. And we will see this will be interesting, useful later on. We will see an application for theorems about that. So the first theorem in symplectic geometry, the Marsden-Weinstein-Meyer Theorem. So it says, if we have a Hamiltonian G space for compactly grouped G, and we also suppose that G acts on the zero level set freely, then there will be a natural action that, and we can then consider the orbit space, which is denoted as the reduced space. The orbit space is smooth manifold. This is basically by the quotient manifold theorem, some big group theory. And we denote the projection from the original manifold to the quotient manifold as pi. And this is a principal G bundle. And the theorem also says that there is a symplectic form for this reduced space. This is called the reduced form, denoted by omega reduced. I will not talk about the proof of that theorem. That's due to some Lie group theory, including the Cauchy-Manifold theorem, the correspondence between the Lie subgroups and Lie subalgebras, etc. And these are two theorems giving more Hamiltonian G spaces. Well, I already wrote them down here because I will use them later. The first one is the commuting action. Suppose we have the Hamiltonian G space, and there's another Lie group acting that, which commutes with the original Lie group. And also we suppose the moment map is G invariant. Then there will be, then the reduced space is not just a symplectic manifold. We have a Hamiltonian H structure for that reduced space. And the second one is Lie group action, subgroup action, where you restrict this G to a closed submanifold of the original Lie group. So by Cartan, this is a Lie subgroup, and then you restrict that to get a new moment map. This is the first concrete example of Hamiltonian G space I will talk about here. Sorry, the second one. This is the complex projective space. So we already know there are complex structures for that. These are the complex charts where phi is the homogeneous coordinates from charts to Cn. And there's a result showing that there's a natural Euler form in Cn. We can define, and we can pull back this form using this phi to phi omega. Let this be omega I. And we can show that for each of the intersection between I and J, these two pullbacks are the same. They agree with each other. And this will then give a global symplectic form on the complex projective space, because we can simply glue them together. And for every intersection, they are the same. This is called the Fubini-Sturi form. And we now consider two actions for this complex projective space. So our base manifold is this. Oh, sorry, our basic manifold is this. Here, omega 0 is the standard form, and we have two actions. First one is by circle action. Second one is by the toral action. The action is simply to pointwise rotate for each of the coordinates, for each of these coordinates. Their moment maps is given here. I will denote this group as G, this as H. Moment maps and actions. Now, if we verify these two conditions, commutation condition and G invariance condition, we will see that they are true. And therefore, by this theorem of commuting actions, there will be a new structure for the reduced space. Hamiltonian structure. And we also know that this 2n+1 dimension sphere is the zero level set. And we know that this can be shown to be, this is the cover view of the CPN. And we have the Guillemin-Sternberg form. We can show that this is there is a symplectal morphism between these two structures. And therefore, there is an induced moment, Hamiltonian H space structure for the complex projective space. Therefore, complex projective spaces are Hamiltonian.
To exclude the zero, this one, that.
Oh, right. Yeah. Sorry about that. Yeah. Thanks. Then the second theorem, Atiyah-Guillemin-Sternberg Theorem. So we recall from our Lever theory course that every compact connected abelian group is a torus of some periods. And Atiyah-Guillemin-Sternberg theorem says if we are given such a group and a compact connected symplectic manifold and the Hamiltonian G-space structures, then there will be three consequences. The connectedness result, the convexity result, and so the first one says that each of the level of the moment map is connected. The second one says that the image of the moment map is convex. And the third says that it is not just convex, the supporting vertices for the convex whole are the image of the fixed point of the actions. So this is called the moment polytope. So we come back to our first example, the circle action on the sphere. And we know that the height function is the moment map, and the north pole and south pole are fixed by this rotation. It is not rotated. And their images are 1 and -1. They are the supporting vertices for this whole image. The whole image is -1 to 1. This is of course convex because in R connectedness implies convexity. So this verifies the Atiyah-Guillemin-Sternberg theorem. Well, I would do an amusing example here, so to address larger audiences. So what are those torus? The one-dimensional torus is just a circle. The two-dimensional one is to copy that. A Euclidean embedding. Well, sorry, a Euclidean visualization for that is this, a donut. It's obtained by this identification. 3 torus, 3 copy of circle. And analogously, I want to say it is the identification of the cube. We identify the back and the front, left and right, top and bottom to get the 3 torus. And we will see that if we position a small person in this room, the person sees the front. Suppose there's light. There's a light. This is the moment that colored chalk will be entered. There's a light going to the front. This light, due to the identification, when it hits this wall, it will go back from the back to here. So the person actually sees the back of his head. And this is the sketch of the proof of the Atiyah-Guillemin-Sternberg theorem. So there are three statements, and the last two are the convexity results. So Atiyah did this using the induction over the periods of the torus. And so we just denote the first and second statement as AM and BM. And the base case for AM is a non-trivial result in Morse theory using a generalization of the Morse function called the Morse-Born function. And you can check the induction proof, which is also involved in Dove's book, Introduction to Symplectic Topology. And we will show the base cases and the inductions for the second statement, convexity result. So the base case is trivial in that in R, connectedness implies convexity. This is because connectedness are just path connectedness, and lines are just paths. And the induction is to think about an injective matrix A with integer entries. So this map can be thought as from Rm minus 1 to Rm, or it's some kind of quotient from the torus to the torus. And to do the induction, we want to find a less one-dimensional Hamiltonian G-space and apply the Atiyah-Guillemin-Sternberg theorem, the induction hypothesis. And this is this n-1 subtorial action defined by using the original Hamiltonian G-space action. And if you want to see the proof why this is the Hamiltonian action, you can ask me at the end. Okay. So that is a n-1 total action. How to use that to show the original point. For any of the points in this level set, this new moment map, you see that another point is also in this. If and only if this maps P to this level, which means which implies that the level set are spaces of this form. And then we apply the Atiyah-Guillemin-Sternberg theorem, the induction hypothesis. This level set is less one-dimensional than the induction hypothesis that says that S should be connected. So this set is connected. And you consider paths in this set, it will necessarily enforce the convex combination of these 2 points to be still within this set. And therefore, this is convex. And for general points in the level set, sorry, symplectic manifold M, you can consider some approximations to these 2 points by 2 sequences. And we can also assume these sequences have rational entries. The approximation is due to compactness. And then there are some technical details. If you want to see that, you can also ask me at the end. I will show 2 examples for Atiyah-Guillemin-Sternberg theorem. The first one is the action that I just talked about, the m plus 1 dimensional toric action on the complex projective space with the Fubini-Study form with this induced moment map. And this is its moment map written explicitly. This is its moment polytope when n equals to 2. It's a simplex. And we also have a less one-dimensional toric action on the same space. For this one, we do all of the others as circle actions similarly, but leave the first homogeneous coordinate fixed, unchanged. This action has such moment polytopes in these spheres. They are simplices too. Then the third theorem, last one. The Delzant classification with the symplectic toric manifolds. So an action of the group G on a manifold M is said to be effective if each of the group element moves at least 1 point in it. So the intersection of the stabilizers is only the identity. And theorem says that if we have the Hamiltonian toric action, and if the action is effective, then the interesting thing is that the dimension of the symplectic manifold is at least twice of the periods of the torus. What if the equality holds? When the equality holds, we call that manifold to be a symplectic toric manifold. And then we come back to our examples of the complex projective spaces. So we have 2 actions, the n plus 1 action or CP, and the less one-dimensional action or CP. And so this first action is not effective. That's because the subgroup of this element of this terms, where all of these elements are the same. If you do the action, since this is homogeneous coordinates, homogeneity means if you put that out, this will equal to itself. Therefore, these points are fixed. So this diagonal subgroup acts trivially on this manifold. Therefore, it does not satisfy the requirement that all of the stabilizer is only the identity. But the second one, the second action is an effective one, as you can check that. And we also see that this has dimension n, this has dimension 2n. So the dimensionality also holds. Therefore, although CPN is not a symplectic toric manifold by this action, it is a symplectic toric manifold by this action. And Delzant classifies all of these symplectic toric manifolds combinatorially. So a unimodular polytope or a Delzant polytope is a polytope satisfying three conditions here. I will do a two-dimensional example here. So for R2, for each of the, for this polytope, we see for each of the vertex, it has two edges meeting together. And each of these vectors should span the whole Z2 lattice points. And this looks well trivial, but for example, let us look at this example, this triangle. So simplicity is of course true. How about the smoothness? Check this one for this vertex. This two does not span the whole lattice point. Because such vertices, such points will basically missed, although these points are spanned by these two edges. And just like what I have said about the classification, every time when we define a new object, we want to say how to say the two objects are the same. So this is by the symplectic toric isomorphisms. So it is of course, a symplectomorphism that is also equivariant naturally. And then this is the Delzant classification. It says there's a one-to-one correspondence between the spaces of all of the symplectic toric manifolds and all of the Delzant polytopes, modulo the symplectic toric isomorphisms and translations of this Delzant polytopes. If you have a question about why isomorphisms give translations of polytopes, the images of these symplectic manifolds, you can ask me at the end. And the proof of this theorem is by three steps. The first one is, of course, to say this map is well defined, which is to say for each of the symplectic toric manifold, its image is indeed a Delzant polytope. The second one is that this map is surjective, which is to say for each of the Delzant polytope, you can find a symplectic toric manifold so that the moment map, the image of the moment map of it is the given Delzant polytope. The last one is injectivity. So this one is by Delzant. The last one, I saw the proof by Lermans. So then we go to the last part, application and generalizations. So this first application, not really an application because historically, Schur-Horn theorem is the primal inspiration for Atiyah-Guillemin-Sternberg to think about this convexity result of symplectic manifold. And an elementary proof of that will be involving a lot of matrix computations. And one way to simplify that is to use the Birkhoff-von Neumann theorem to do one direction, which says any bistochastic matrix, the matrix with rows and columns all sum to 1. Any of the bistochastic matrix is a convex combination of the permutation matrices. So if you have a drawing, a polytope, where each of the vertex is the permutation matrix, then the convex whole generated by these vertices, denoted by P, for example, then the bistochastic matrix should lie inside here. The Atiyah-Guillemin-Sternberg theorem can give a very high level viewpoint on this Schur-Horn theorem.
So what is H? The T map from H to
The H is the Hermitian matrices. So we can consider the unitary group acting on Hermitian matrices by conjugations. And there's also, so these actions is a group representation. And there's also the other group representation, which is the coadjoint representations that we defined at the beginning of this presentation. And these two, we have two group representations, and we have a natural intertwining operator, the linear isomorphism between these two vector spaces. And therefore, this will borrow the KKS form, the Kirillov-Koryu constant serial form. Borrow that form on the coadjoint orbits back to the orbits for the unitary action on the Hermitian manifold. Sorry, Hermitians. The orbits are denoted by this. And then this is symplectic manifold, and you can apply Atiyah-Guillemin-Sternberg theorem to this manifold. And it will give the result on the Schur-Horn lemma, theorem. And there are more general Hermitian spectra problems considered by Knuston and Tao, and they use algebraic and combinatorial tools for that. For example, this is the honeycomb they used. And Knuston used in his paper the following Kirwan's generalization of Atiyah-Guillemin-Sternberg theorem for the non-abelian groups. Recall that AGS theorem is about the abelian connected common groups. Here they are the non-commutative papers. And Weinstein generalized that to the non-compact cases. This is just a historical review. I will not talk about the definition of wild chamber. That's included in the algebra. And the last one is the last application, the geometric representation. The Kirillov constant serial form is a canonical way to give a symplectic form for each of the coadjoint orbits. Coadjoint orbits are just the orbits of the coadjoint actions. And there are symplectic toric manifolds. These are the two basic objects we talked about. Now suppose we have a symplectic manifold M and we say this symplectic manifold is pre-quantizable. If there is a Hermitian line bundle over that, so that the curvature form of that is omega. And the theory of geometric quantization is concerned with the problem of quantizing M by attaching to it a pre-quantum Hilbert space QM. This one, satisfying several axioms. I will not talk about how to do this pre-quantization or the existence of such quantization or the uniqueness of that. We will simply assume that for the spaces we are interested in, they're there. These axioms are multiplicity, duality, finiteness, and functoriality. These are natural algebraic arguments you can consider. And for the functoriality, this is an interesting one. So for a compactly group G, there is for every Hamiltonian action, Hamiltonian G action, there is a unitary representation from G on the Hilbert space. And constants have a nice formulation of this functoriality, well, Bolt-Borel-Weil theorem is a nice illustration of this functoriality axiom, and constant has a nice formulation of that. Here it is. So for a compact and connected elite group, there's one-to-one correspondence between the irreducible unitary representation of the group G and the pre-quantizable coadjoint orbits. And there is a last axiom for that pre-quantum Hilbert space, which is the reduction one. So for a Hamiltonian G space, and you have a reduced space from the zero level set, and you're given with a corresponded, you're given a coadjoint, pre-quantizable coadjoint orbit. Then there's a corresponded Bolt-Borel-Weil representation, and then you can denote QMG as the invariant space, fixing the space fixed by all of this transformations. Then the axiom is that the pre-quantum Hilbert space you associate with the reduced space is the same as this invariant subspace. And Guillemin and Sternberg proposed a counting formula on those corresponded unitary irreducible representations. And before that, we recall the familiar version of the Schur's lemma in finite-dimensional vector spaces over a complex number field. The lemma says that the subspace, well, the collection of all of the intertwining operatives between given irreducible representations relative B of any group G, and this collection is a subspace. It's a subspace from V to W. Well, V is well, we can write this to representations as the homomorphisms sending to the general linear group of V and W. And this collection of all of the intertwining operatives is actually the subspace of the homomorphisms between V and W. And Schur's lemma says that okay, this subspace is null, is zero, if these two irreducible representations are not equivalent. And if these two representations are the same, then this subspace is one-dimensional. And the interesting thing is that this result, the requirements of a finite dimensional vector space over the complex vector pairs are only used for the second one. The first one does not use that. And this can be generalized to any of the finite dimensional vector spaces over the algebraically closed fields. Okay. And there's also an analog for the Hilbert space representation here. Right. So for the Hilbert space representations, you need those operators to be bounded or continuous. Then there's the conjecture by Guillemin and Sternberg, the multiplicity conjecture. So let's let this O be a pre-quantizable coadjoint orbit. Then we have this corresponding irreducible initial representation. Let this rho be the representation in the functoriality axiom. And then this be the pure where you reverse the KKS form for this coadjoint orbit. And let MO denoting the reduced space of this product manifold. Then we have some computations here. This twisted or reversed coadjoint orbit by the second axiom of the pre-quantization is the dual. And this product manifold, the Hilbert space for that is denoted by this tensor product, which is this. And the last axiom, the reduction axiom, is that we have this. These are basic algebraic arguments, computations. And so we have a representation rho, and we want to ask how many, because every representation can be written, we can write this as forms like this. These are the irreducible representation. Irreducible means you cannot reduce it anymore. And we want to count how many of this irreducible representation is appear in this decomposition. This is the multiplicity. Each of these mi is called multiplicity. So Schur's lemma says that dimension of this, which is equal to the dimension of this, Schur's lemma says this is equal to the multiplicity of O. And now Sternberg and Guillemin conjectured that for the compact connected Lie group G and Hamiltonian G space and this product manifold and its reduced space, the multiplicity of rho O in this rho is equal to the Riemann-Roch number of this reduced space. And Guillemin and Sternberg proposed that conjecture in a paper in 1982. And they verified that it is true for the toric case, where you have these settings. And well, due to the time limit, I will not talk about the details for this, but you can see that in the toric settings, the reduced space MO is equal to M delta, where M delta is Delzant's construction of a symplectic manifold, so that its moment polytope is the Delzant polytope here given. And
So I'm a little lost. What is the rho zero again?
this is from the functoriality here, rho.
Oh,
For every Hamiltonian G action, you have a unitary representation. And we want to count the BBW, the number of that BBW representation in that row. And they verify that in the toric case. Why? Because the right-hand side is defined using the chain class, and you can use that to define the top class, and then this will be shown to be equal to this. And there is the left-hand side can be shown to be the multiplicity of this is O, because in one dimension case, this coadjoint orbits for this action, these coadjoint orbits are just constants. Counting this is the number of the integer points in that Delzant polytope.
I'm sorry.
Yeah, the
10 minutes over. I need to really start.
And then the two Russian says that this is equal to each other. And so multiplicity conjecture is true for the symplectic toric case. And this was true generally by Marsden-Weinstein and Tao and Zhang later in 1990s. Oh, okay, and this is called the quantization commutes with reduction conjecture. This is references and any question.
Okay. Let's talk. So, any questions, comments?
I have a few questions, but I have to run to a meeting, so I might have to ask you, but I was maybe just put it out there, so I wonder if the lattice points right inside the polytope is that does that correspond to spectrum of some operators? Are those values of something? These are simply to count to obtain some integer that gives the. I wonder if there's some significance to those integer points in terms of operators.
I don't know.
Doesn't come up. I have to run, but it's very nice, very good.
Sorry.
Do I have to sign?
No, I don't think it's signature. So, Laura, are you still around?
Document.
Oh,
Oh, people leave.
okay, so. Okay, so any other questions? There's no question. Let's thank Anthony again for